Welcome to The Explainer. So, have you ever looked at an AI and just wondered, how does it do that? How can it take a few bits of information and then, boom, make a prediction that's shockingly accurate? Well, today we're going to pull back the curtain on exactly how that works. It all boils down to a really simple question. Let's say you give a computer a handful of data points. Just a few dots on a graph. How on earth does it go from just seeing those dots to actually understanding the pattern behind them? All right, so here's our challenge. We've got just 4 data points. Super simple. When x is 1, y is 3. When x is 2, y is 7. You get the idea. Our mission is to teach a machine to find the hidden rule that connects x and y. Okay, so we've got our data. But before we just dive in and start crunching numbers, we need to be really, really clear on what we're trying to do. What does winning this prediction game even look like? See, the goal here is way more than just a game of connect the dots. Anyone can do that. The real challenge, the magic of it really, is finding that one smooth curve that not only hits the points we have, but can also tell us, with confidence, where the next dot is going to land. We want it to predict the future.
So out of all the infinite possible curves in the universe, how do we find that one perfect fit? Well, this isn't about guesswork. We're going to use some powerful math to calculate it directly.
And that's a great question, right? Is there really just one formula that can spit out the best curve every single time? For this kind of problem, the answer is a big, resounding yes. No trial and error needed.
And here it is. This beast is called the normal equation. Now, don't worry about all the Greek letters and symbols. Honestly, just think of it as a super-powered calculator. You feed in your data, it does its thing, and it directly calculates the exact numbers that define the one single curve that fits best. It's a direct shot to the answer. So, the process itself is pretty straightforward. First, you take your data and organize it into this special grid called a design matrix. It's just a neat way to line up your numbers. Then, you plug that matrix into the normal equation. And finally, you solve for W. These are the model's weights. Just think of the weights as the secret sauce, the numbers that give our curve its unique shape. And after we run our 4 little data points through that whole process, this is what pops out. Look at that! A clean, simple formula. The normal equation tells us this is the single best mathematical way to describe our dots.
And if you plot this out, it's perfect. The curve goes straight through every single one of our data points. Mission accomplished, right? Total success. Or is it? Because in machine learning, sometimes being too perfect is a huge red flag. And that brings us right to something called the overfitting trap. Let's dig into how this perfect success can actually be a massive problem.
So this really gets to a core idea in all of machine learning. What happens when a model is too good? What's the danger when it doesn't just learn the pattern, but it memorizes every single little detail, every little quirk in the data?
Well, that's called overfitting. And it's like a student who crams for a final by memorizing the answers to the practice test. Sure, they'll get 100% on that specific test, but give them the real exam with slightly different questions, they're going to fail, big time. They never actually learned the concepts. Our model has basically done the same thing here.
This slide lays it out perfectly. On the left, you've got what we want, a model that learns the general trend. It's simple, it's smooth, and it's great at predicting new points. But on the right, you've got our overfit model. It's this crazy, complex, wiggly curve that's twisted itself to hit every single point. It's a master of the past, but it's totally useless for telling us anything about the future.
Okay, so how do we stop our model from trying to be this perfect memorizer? We need to give it some rules. We need to penalize it for being too complex. Basically, we have to put it on a leash. And the technique for this is called regularization. It is, no joke, a cornerstone of modern machine learning. It's basically a set of rules we add to the process that push the model towards simpler solutions. It's built on a super old scientific idea. The simplest explanation is probably the best one.
Now, one of the most common ways to do this is called ridge regularization, and all that math on the slide boils down to a really simple rule. It's like telling the model, hey, go ahead and find a great curve, but you have a complexity budget. The numbers that define your shape, your weights, can't get too big and crazy. You have to stay under this limit.
And the logic for finding this smarter solution is actually really elegant. First, the algorithm finds that perfect overfit answer we saw before. Then it just asks a simple question. Is this solution within my budget? If the answer is yes, great, we use it. But if it's too complex, if it's over budget, the algorithm just pulls it back until it's sitting right on the edge of what's allowed. It finds the absolute best model that still plays by the rules of simplicity. And result? A model that's way more reliable. By forcing it to be simpler, we've basically made it ignore the random noise and focus only on the true underlying pattern. So yeah, we trade a little bit of perfection on the data we've already seen for much, much better prediction power on new data it's never encountered.
All right, so let's zoom out. What does this whole journey, from a few dots on a graph to a smart, constrained model, really tell us about machine learning in general?
Because this whole process we just walked through, fitting a model, realizing it's overfitting, and then adding a constraint to make it smarter, that isn't just one little trick. This is the fundamental cycle of how you build intelligent, reliable AI. So, what are the big takeaways? First, deep down, a lot of machine learning is just a really fancy version of curve fitting. But more than that, building a good model means you have to understand your data, you have to actively fight overfitting with tools like regularization, and, this is crucial, you always have to test your model on fresh data to make sure it's actually learned something, not just memorize the answers.
And that really leaves us with a final important question to chew on. When we're building AI, is the real goal to find the perfect answer or the most useful one? Because chasing mathematical perfection can lead you down the wrong path. The real art and science here is finding that balance, building something that isn't just perfect on paper, but is genuinely, powerfully, and reliably useful in the real world.